The relational model can handle simple cases of many to many relationships. But as the connections within your data become more complex, it becomes more natural to start modeling your data as a graph. A graph consists of two kinds of objects: vertices, which are also known as nodes or entities, and edges, which are also known as relationships or arcs. Graphs are not only limited to homogeneous data. Facebook maintains a single graph with many different types of vertices and edges. Vertices represent people, locations, events, check ins, and comments made by users, whereas edges indicate which people are friends with each other, which check in happened in which location, and so on. Now, we'll discuss different types of graph models, and the first one is property graphs. So, in the property graph model, each vertex consists of a unique identifier, a set of outgoing edges, a set of incoming edges, and a collection of properties, which is basically key value pairs. And each edge, now let's say that this is an edge. Each edge consists of a unique identifier, the vertex at which the edge starts, the tail vertex, the vertex at which the edge ends, the head vertex, a label to describe the kind of relationship between the two vertices. So let's say that these two vertices represent two people and they're married. So the label of the edge would be married. And then a collection of properties. So when were they married, where were they married, and so on. So you can think of a graph store as consisting of two relational tables, one for vertices and one for edges. So here are the two tables. Now the head and tail vertex are stored for each edge. If you want the set of incoming or outgoing edges for a vertex, you can query the edges table by head vertex or tail vertex respectively. Any vertex can have an edge connecting it with any other vertex. There is no schema that restricts which kind of things can or cannot be associated. Given any vertex, you can efficiently find both its incoming and outgoing edges and thus traverse the graph. By using different labels for different kinds of relationships, you can store several different kinds of information in a single graph while still maintaining a clean data model. You can think of a graph store as consisting of two relational tables, one for vertices and one for edges. So here are the two tables. This is for vertices and this is for edges. So the head and tail vertex are stored for each edge. If you want the set of incoming or outgoing edges for a vertex, you can query the edges table by head vertex or tail vertex respectively. Any vertex can have an edge connecting with any other vertex. There is no schema that restricts which kinds of things can or cannot be associated. Given any vertex, you can efficiently find both its incoming and outgoing edges and thus traverse the graph. By using different labels for different kinds of relationships, you can store several different kinds of information in a single graph while still maintaining a clean data model. Now, this figure displays two people, Lucy from Idaho and Elaine from Beyond France. Now they're married and they live in London. So Lucy also lives in London and Elaine also lives in London. So it shows a few things that would be difficult to express in a traditional relational schema, such as different kinds of regional structures in different countries. So France has departments and regions, whereas US has country and state. So, and there are much more examples here which would be difficult to express in a traditional schema. The Cypher query language. So, Cypher is a declarative query language for property graphs created for the Neo4j database. Now, let's look at this diagram again. We saw this diagram in the previous video, and as a summary, this is a graphical representation of data of two people, Lucy and Elaine. Now, we'll insert the left-hand portion of this diagram in the graph database using Cypher language. So as you can see here, these are vertices in a graph database, and each vertex has been given a unique name. Here the name is Idaho, here the name is United States, and so on. So the query of Cypher language also inserts the vertices into the database, like we are inserting North America here, United States, and so on. And the other parts of the queries can use these names to create edges between the vertices using an arrow notation like this. So this arrow notation basically creates an edge labeled as within, with Idaho as the tail node and USA as the head node. So basically like this. This is Idaho and this is USA, and here it is being labeled as within. Now let's see one more example. So let's find out the names of all the people who emigrated from the United States to Europe. Now what this question means is find all the vertices that have a born in edge to a location within the US and also a living in edge to a location within Europe. So basically, people emigrated from the United States to Europe means that the people should have been born in the United States and should be living in Europe. And then you return the intersection of that. So we'll use the same arrow notation using a match clause. So basically, this arrow notation, person born in and then empty parenthesis, matches any two vertices that are related by an edge labeled as born in. Now let's look at this query. So this query can be read as follows. So this first line would mean that find any vertex, and let's call it person, that meets both of the following conditions, this and this one. So let's read out the first condition. So basically a person has an outgoing edge as born in to some vertex. And then from that vertex, you can follow a chain of outgoing within edges until eventually you reach a vertex of type location whose name property is equal to United States. Similarly, now you find a person who has an outgoing lives in edge to some vertex. And from that vertex, you can follow a chain of outgoing within edges until eventually you reach a vertex of type location whose name property is equal to Europe. And then you return the name of the person. Now, there are several possible ways of executing the query, but as is typical of the declarative languages, you don't need to specify the execution details when writing the query. The query optimizer automatically chooses the strategy predicted to the most efficient. Graph queries in SQL. So we saw that the graph data structure can be represented in a relational database. But if we put graph data in a relational structure, can we also query it using SQL? Yes. In a relational database, you usually know in advance which joins you need in your query. In a graph query, you may need to traverse a variable number of edges before you find the vertex you're looking for. That is, the number of joins is not fixed in advance. In Cypher, this notation within *0 expresses that fact very concisely. It means follow a within edge 0 or more times. It is like the star operator in a regular expression. So since SQL 1999, this idea of variable length traversal paths in a query can be expressed using something called recursive common table expressions, the with recursive syntax. Now let's talk about a different way of representing graph data, that is triple store and Sparkle. So in a triple store, all information is stored in the form of very simple three-part statements: subject, predicate, and object. For example, in the triple Jim likes bananas, Jim is the subject, likes is the predicate, and bananas is the object. So the subject of a triple is equivalent to a vertex in a graph, and the object can be one of these two things: a value in a primitive data type such as a string or a number. In that case, the predicate and object of the triple are equivalent to the key and value of a property on the subject vertex. For example, Lucy age 33 is like a vertex, Lucy with properties age 33. Now, an object can also be another vertex in the graph. In that case, the predicate is an edge in the graph, the subject is the tail vertex, and the object is the head vertex. For example, in Lucy married to Elaine, the subject and object Lucy and Elaine are both vertices, and predicate married to is the label of the edge that connects them. Now, this example shows a subset of Lucy and Idaho's data written as triples in the turtle format. So here you can see that it says Lucy is a person. Lucy name Lucy. Lucy is born in Idaho, and so on. So in this example, vertices of the graph are written as some name. The name doesn't mean anything outside of this file. It exists only because we otherwise wouldn't know which triples refer to the same vertex. So all of these vertices are for Lucy. Now, when the predicate represents an edge, the object is a vertex, as in Idaho is within USA. When the predicate is a property, the object is a string literal, as in USA, name is United States. Now, a more concise way to represent this data is like this. This is the turtle format. So you can say that Lucy is one vertex and all of these are the properties. She is a person, her name is Lucy, she is born in Idaho, and so on. The semantic web. So the semantic web is fundamentally a simple and reasonable idea. Websites already publish information as text and pictures for humans to read. So why don't they also publish information as machine readable data for computers to read? So the Resource Description Framework, RDF, was intended as a mechanism for different websites to publish data in a consistent format, allowing data from different websites to be automatically combined into a web of data, a kind of internet-wide database for everything. Triples can be a good internal data model for applications, even if we have no interest in publishing RDF data on a semantic web.